All right, so today we are going to cover genetics math. So, there's a word that you will see come up sometimes that is hybrid. And in terms of genetics, what this means, it refers to a heterozygote. Okay. Sometimes you might also see some other terms associated with this. You might see something called wild type versus mutant. Okay, the wild type generally refers to the most common allele that you'd find in the wild. Or the most common allele naturally. And then the mutant would be some new allele or some different allele that it goes into that same spot. Okay, so one of the things that we will see is something that's called a monohybrid cross. And that is with two parents that are each heterozygous for the trait. Okay, so that would be like big A crossed with big A. Or big A, little a. Big A, little a crossed with big A, little a. Sorry. So if we did this in a Punnett square, it would look like this. Big A, little a, big A, little a. And then we run them through the Punnett square. Like so. Right? All familiar with this process? Yeah? Good? All right. So let's look at the phenotypes here. Our phenotypes are dominant A and recessive A. Those are our only two phenotypes. So what percentage here? So here's dominant A. Which percentage or which boxes are dominant for A? 75%, or these three boxes. Right? So we would say 3 out of 4, 75%. The recessive A is this box only, and that is 1 out of 4, which is 25%. So we say that our phenotypic ratio here is 3 to 1, dominant to recessive, 3 to 1. Yeah, so 3 of these, 1 of these, 3 to 1 phenotypic ratio. Yeah, good. All right, let's look at genotypes. In this case, we have 3 genotypes possible. We have big A, we got big A, and we got little a. How many big A's? 1 out of 4. Big A, little a? 2 out of 4. And little a? 1 out of 4. All good? Easy peasy? All right, let's talk about a dihybrid cross. A dihybrid cross is parents that are heterozygous for two traits. So in other words, we'd have like big A, big B, little b, crossed with big A, big B, little b. Okay, so we need to look at the gametes produced. Okay, gametes are produced via the law of independent assortment, right? And the way that we figure out the gametes is by foiling. So if I have big A, big B, little b, I'm going to do first, that would be big A, big B. Outside, that would be big A, little b. Inside, little a, big B. Last, little a, little b. These are the gametes that are produced by this parent, okay, or the combinations of alleles that would be in the gametes, assuming normal meiosis, assuming no crossing over, or assuming that no gene linkage, rather. Yeah? Good? Okay. To do a Punnett square for this, I'm going to take these gametes and I'm going to put them in the individual spots. And then I'm going to run them through. So just going to go ahead and do it, the whole thing. Oh yeah, we should never do this, but I'm going to do it for today. This is a terrible plan, but we're going to do it for the purpose of discussion. All right, so I got different phenotype combinations. In this case, I've got dominant A, dominant B. I've got dominant A, recessive B. I've got recessive A, dominant B. And I've got recessive A, recessive B. Okay, so let's figure them out. So here's my, that one's this one, that 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 one. I think that's it. So I count them up. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 16 total boxes. So that's 9 out of 16. Next one is dominant for A, recessive for B. So dominant A, recessive B, dominant A, recessive B, dominant A, recessive B. So that would be 3. 3 out of 16 would have that. And then I got recessive A, dominant B. So that's this guy, and this guy. So that's, again, 3 out of 16 for that. And then finally, recessive A, recessive B. (1/16). So my phenotypic ratio that I would expect in a dihybrid cross is 9 to 3 to 3 to 1. Now, I could go through and do the individual probabilities of the genotypes, but I'm not going to. That would take a long time. Okay? Good so far? Feeling good? All right. Let's talk about the multiplication rule for or of probability. All right, multiplication rule says this: the probability of two independent events occurring is the product of each event's individual probability. Okay, so what is the probability of parents with genotypes big A, big B, little b, and big A, big B, little b, producing offspring with the dominant A, recessive B phenotype. Oh, we just did that, right? That's a dihybrid cross. So dominant for A, recessive for B, we said was what? 3/16, right? So we know from the Punnett square, from the 4x4 Punnett square, that would be 3/16. But we can do this much easier. All we need to do, because that took making this whole Punnett square, right, And what we can do is we can just say, all right, let's look at the probability that they'll get dominant phenotype plus, and then the dominant that they'll get, or the probability they'll get the recessive phenotype. So up here in a monohybrid cross, we know 3 out of 4 will have the dominant and 1 out of 4 will have the recessive, right? So we can break down a dihybrid cross into 2 monohybrid crosses. So we can say that the probability that you'd be dominant for A is 3 out of 4. And the probability that you're recessive for B is 1 out of 4. So the probability that you are dominant for A and recessive for B, 3 times 1 is 3. 4 times 4, 16, is 3/16. Right? Let's take it a step further, right? Let's say, what is the probability they are big A, big B, little b? So we go look at our 4x4 Punnett square. Big A, big B, little b. So there's a big A, big B, little b here. Big A, big B, little b here. Any other ones? It's just these 2 spots right here. So that's anywhere else? No. So that's 2 out of 16, right? So that would be 2 out of 16 squares have that. All right, so now let's look at probability that they would have big A, and the probability that they would have big B, little b. So we go up at our monohybrid cross. What's the probability of big A? 1/4, and big B, little b? 2/4. 1/4 times 2/4 gets you 2/16. All right, do we start to see the value here? Yeah. No. Improper fractions and non-reduced fractions are totally fine. Okay, what's up? No, it would be fine. All right, so what is the probability that parents with the genotypes big A, big B, big C, little c, and big A, big B, big C, little c, will produce offspring that are dominant A, recessive B, dominant C. Okay, so now we've got a tri-hybrid cross, which we would need an 8x8 Punnett square for. We'd need 64 boxes. Should we do that? Yes. No, never do that. That is ridiculous. So we can just do a couple of small Punnett squares. We can't rely on our monohybrid cross here because they're not all monohybrid crosses. Our first one we can see is big A, and then big A, little a. Okay. Our second one is a monohybrid cross. It's big B, little b, big B, little b. Oops. And then the third one, another monohybrid cross. Okay, so what is the probability that you're dominant for A? It's 4 out of 4. Okay. What about dominant? Oh no, sorry, recessive for B. Hang on. So dominant A, recessive B would be 1 out of 4. And then dominant for C, 3 out of 4. So we got 4 times 1 times 3 is 12. 4 times 4 is 16 times 4 is 64. 12/64 would be that probability. No, that would be fine. So, what do we think? Easy? Simplifies things a lot? Especially, what if it didn't ask for dominant A, recessive B, dominant C? What if it asked for the probability of big A, little a, big B, little c, little c? Well, now you're like, whoa, I definitely need to do this Punnett square. And you're like, nope, I don't, because big A, little a was 2 out of 4. Big B was 1 out of 4. And little c was 1 out of 4. And you get 2/64. Okay? So, what if we're looking at a large-scale experiment with 3 traits, right? And we get 100, no, let's just, for the purpose of discussion, let's just say there are 64 total offspring, right? And of our 64 offspring, let's say 15 of them are dominant A, recessive B, dominant C. But we were expecting 12, but it's 15. Does that indicate to us that there's something weird going on? That there's some underlying genetic thing going on? Johnny, what do you think?
I don't think it's statistically significant enough.
I like that. All right. So the point is, our little human brains, we try to see patterns in everything. And so we say, oh, we were expecting 12, but instead it was 15, right? Or, you know, people who drink Ovaltine score higher on the SAT or something like that. But in actuality, that might not be the case. If you only have 64 offspring that you're studying and you're only off by 3 from your probability, there's a very good chance that that is the result of random chance, right? If you flip a coin 10 times, sometimes you'll get 10 heads in a row. That may or may not mean that the coin is unfair. If you flip a coin 2 times and you get 2 heads in a row, can you tell anything from that? No. If you flip a coin 1,000 times and you get 700 heads, now what? Now we're starting to get into some weird area. We're like, okay, well, it should be 500, but we got 700. Is that enough? Is that statistically significant to say that there is something else going on here that's not random chance? And we use something called chi-square for that. Chi-square analysis basically figures out if what we're looking at is due to random chance or not random chance. And so tomorrow what we're going to do is we're going to take this, knowing how to get the expected outcomes or the probabilities, and we're going to compare it to actual outcomes and figure out if they are due to random chance or not random chance. Okay? Anyone have questions on this? Easy enough? Awesome.